Number 25, a rocket is launched from the surface of a planet with mass big M and radius big R. What's the minimum velocity the rocket must be given to completely escape from the planet's gravitational field? So we're really looking for the escape velocity. All right. So for the escape velocity, we could say that the rocket initially has a kinetic energy plus a gravitational potential energy initially. And that's going to equal its kinetic energy and its gravitational potential energy at infinity. Now we're saying its kinetic energy at infinity should be zero. That should go to zero. It should have no more velocity once it gets to infinity. And when we define gravitational potential energy, we say it too has no gravitational potential energy at infinity. So that whole right side of the equation is going to be equal to zero. So we would have 1/2 mv squared, and this is the escape velocity, minus gravitational potential energy equation, big G times big M, little m over R, and that's going to equal 0. All right, so let's keep velocity on one side and put the gravitational potential energy on the other side, big G, big M, little m over little r. Multiply both sides by 2 and divide by mass, and then take the square root. We're going to get the escape velocity equals the square root of 2 times big G, big M, little m over little m times r. The little m's would cancel, so we're left with square root of 2 big G, big M over little r, but in this case they said the radius is big R. So we're going to equal 2gm over r square root. So it looks like C would be our best bet. Wait, 2gm. A is our best bet. 2gm over r square root.